Have you ever noticed that when you take a temperature with a non-digital thermometer, that the temperature jumps up significantly at first and then slowly approaches the temperature but does not overshoot it? In fact, the temperature in the thermometer is going to have a response that looks like an exponential. Another example of a system that behaves this way is a rotating system with an inertia and friction, say a fidget spinner. Notice that the fidget spinner slowly approaches zero angular velocity, but it doesn't overshoot and start going backwards. These types of systems are called first-order systems, and in circuits, the simplest possible first-order system is a circuit with one resistor and one capacitor, an RC circuit. To understand this, it is important to first highlight some facts about capacitors. The first is that it takes time for capacitors to charge or discharge. The second is that if there's no change in voltage, a capacitor looks like an open circuit. What this means is that the change in voltage across a capacitor is going to go from some initial value to some final value, and it's going to take some time to get there. So, the only way for voltage to change across a capacitor is to either flip a switch or for there to be some initial voltage across the capacitor. It turns out that in an RC circuit with a switch, the voltage across the capacitor, V of t, is equal to V of infinity plus square bracket V of 0 minus V of infinity close to square bracket e to the negative t over tau, where V of infinity is the voltage across the capacitor a really long time after the switch is moved. V of 0 is the value of voltage across the capacitor before the switch moves, and tau is the time constant, which is the time it takes for the voltage to travel 63% of the way between the initial and final values. Tau, as it so happens, is equal to the resistance times the capacitance. To illustrate this, let's do an example. We want to find V of t across the capacitor if V of 0, the initial voltage, equals to 0, and the switch closes at t equal to 0. We know that V of t is equal to V of infinity plus square brackets V of 0 minus V of infinity close square brackets e to the negative t over tau. So we need to find each of these, V of infinity, V of 0, and tau. Let's start with V of infinity. We assume a really long time has passed since the switch is closed and the capacitor is completely charged. Since there is no change, the capacitor looks like an open circuit. If the capacitor is an open circuit, there's no voltage drop across the resistor because current is 0. As a result, V of infinity is V source, which is 10 volts. V of 0 was given as 0 volts in the problem statement. Finally, tau equals R times C. This is 5 times 0.1 or 0.5 seconds. Substituting these values into the equation, we get V of t is equal to 10 plus square bracket 0 minus 10 close square bracket times e to the negative t over 0.5, or simply 10 minus 10 times e to the negative 2t volts. So, there really is a straightforward way to describe first-order circuits, and it turns out that first-order systems show up and are very present in our lives. Thank you so much for watching this video. If you feel that I've earned it, I would love it if you would subscribe and possibly share this video with someone else. You can find me on Twitter or Instagram at BD McPheron. For now, this is Dr. McPheron. Keep on keeping on.